Welcome back. Today we're going to be talking about optimization, and more specifically, we're going to be answering this question, which says a farmer has 2,400 feet of fencing and wants to enclose a rectangular area into two pens. What is the largest possible area? So, first of all, since we know it's a rectangular area, I'm going to write down that the area is going to be equal to length times width. And I'm also going to be drawing a picture of what we're describing here. So here we have a rectangular area like that. And then we're dividing it into two separate parts like that. There we go. And then we have two lengths. We have a length here and a length here. And then we also have three widths. This is a bit different from a regular rectangle. Normally we would just have two widths in our rectangle, but here we have three because we're going to need the regular widths that we would normally have for this fence, but we're also going to need the width in the middle that's dividing this rectangular enclosed area into two separate pens. So that's an important key factor to keep in mind. Okay, so therefore, in this case, the 2,400 feet must cover two lengths plus three widths. So 2 lengths plus 3 widths is equal to 2,400. All right, next I'm going to subtract 2 lengths from both sides. So then we're going to get that 3 widths is equal to 2,400 minus 2L. And then if I divide both of these by 3, I get that W is equal to 800 minus 2/3 L. Okay, now I'm going to take this key equation here that I came up with, and I'm going to plug it back into my area equation. Now, I first want to just to briefly discuss why am I going to do that, because ultimately we want to find the largest possible area. So we're trying to optimize area. If we're trying to optimize area, that means we're going to be taking the derivative of the area. And in order to do that, we would ideally like to just have one variable. So rather than trying to differentiate length times width, if we just differentiated with respect to length or with respect to width, that would be a little bit better for us. So that's what I'm going to do here. Okay, so therefore area is equal to length times width, which width in this case, we're going to sub in 800 minus 2/3 L. And then I'm going to multiply and get 800L minus 2/3 L squared. Then I'm going to take the derivative. And for taking the derivative here, I'm just going to be using the power rule. So the derivative is equal to 800 minus 4/3L. Okay, next step is we want, in order to optimize, we always set the first derivative to 0. So I'm going to be setting the derivative of the area to 0 to get that 0 is equal to 800 minus 4/3L. So then if we add 4/3L to both sides, we get 4/3L is equal to 800. And then if I cross multiply, I multiply by 3 and divide by 4. Let's see, we're going to get L is equal to 800 times 3/4. So that is going to make the length equal to 600. So length is 600. Now we know that from this equation here, that width is equal to 800 minus 2/3 times the length. So minus 2/3 times 600, which that's going to be 800 minus 400, which is 400. So therefore the dimensions of length times width would be 24, or actually 240,000 if we multiply those. Because going back up to the area is length times width, which is 600 times 400. So that's going to be 240,000 square feet. And so that is the answer. So therefore, if we optimize, we end up getting that the area would be 240,000 square feet. Now, as always, if you do have any questions about any of that, feel free to let me know down in the comment section, and I'll see you for the next one.